in fact no numbers and no letters. We've codified our existence to bring it down to human size.
What is she making? New generation computer, I presume. Look, the computer. It's moving.
You're right, Rick. Because you're right.
Organic. Small beginnings. There's mud in your eye, pal.
I'm so sorry.
My God.
Between two different 46 biological interactions between two different organisms. These creatures need to bond with a respiratory host.
What do you see? War, poverty, a planet on the brink of collapse. I would argue that God has abandoned us.
It's consuming his organs. But once again, it's killing the host. It's consuming his organs.
Sounds in the 4 to 6,000 hertz range are very harmful for it.
Well, then don't make those sounds.
Yeah.
Hey, can you turn your music down, please? Because I'm having a really hard time.
Whatever.
And I work on designing graphene nanopores to sequence DNA at a single molecule level. So the idea of DNA sequencing is to read the content of your genome. And what you want is a recorder that can read the sequence of your DNA, but for that you need a recorder that is not bigger than the size of a single base. So we are using graphene because graphene is only one atom thin. So we are really doing high technology with very simple methods. So we take a piece of graphite here, we put the graphite onto the scotch tape, we extrude it once, we take a silicon wafer here, in which that we bring into contact with the graphene, we press hard, we end up with a piece of wafer that somewhere has a graphene layer. And then we bring that chip to a transmission electron microscope to burn a nanopore into it. So then we take this chip, we flow on both sides a buffer, and on one side we inject the DNA molecule, and that's what we can record. There are still a few challenges to overcome, but all the technology I mentioned is in the size of this little chip here that could be used by a physician in his office to sequence the DNA of one of his patients in only a few minutes rather than a few days.
Включен мобильный телефон. Он включен именно когда идет вызов. Пока выключен. И сейчас я набираю номер. И смотрите, что будет происходить. Вот он вызов пошел. Смотрите, что теперь. Вызов идет, если вы можете посмотреть.
Watch as this assembly line pumps out tiny machines called micromotors. These micromotors are only a few hundred micrometers long, and they can move when put inside a magnetic field. Scientists propose that micromotors like these could one day deliver drugs inside the body. A popular way to get around is to use a chemical fuel, such as hydrogen peroxide. Materials in the micromotors react with the fuel to produce jets of gas bubbles that push the tiny particles forward. But this approach can introduce toxic compounds into the motor's surroundings. Ditching the fuel and just using an external magnetic field to move the motors avoids these toxicity issues. It's a strategy that's also well suited for biomedical applications because magnetic fields can penetrate the body. Now, a team of researchers at the Chinese University of Hong Kong and Huacheng University of Science and Technology have developed novel magnetic responsive micromotors made of graphene. Researchers can easily attach other molecules to graphene, and the material has a high surface area which makes it attractive for picking up pollutants. The corkscrew shape helps micromotors move in a rotating magnetic field, but it's been challenging to make helical micromotors from graphene until now. To make the micromotors, the team developed a cheap microfluidic method. The team pumps oil through a solution of graphene oxide and magnetic iron oxide, and a solution of sodium alginate. What comes out are tiny corkscrews with an oil droplet head attached to a graphene oxide-based tail, all of which are sealed inside a sodium alginate fiber. The helical motors get their